and I run a weekly science and technology podcast, Diffusion Science Radio. Like and subscribe. If you go to diffusionradio.com, you can buy my shirts from my Etsy store. I've got 15 designs up and 5 more to go. So tonight, I have the privilege of asking the first questions, just to, in case you need some stimulation, but I'm sure you've had lots. So I had a question for you, Dane. Quantum computers, are they digital or analog?
They're analog. There are a range of different ways that you can implement a quantum computer with a quantum system. Some of the more traditional ones are probably best classified as analog, but there are quite a lot of very creative people who come up with very weird and wonderful ways to implement quantum information processing. The weirdest one I know of is one where you shoot a whole train of photons one at a time, and you start to interact them with each other one by one. And you can build up entangled systems where the last photon of millions of photons in a bunch is entangled with the first photon in that bunch, but that photon doesn't exist anymore. In fact, it died many, many microseconds ago. And so it's a very strange way to think about quantum information, but it's a hard question to answer given everyone has their favorite version.
Thank you. All right, and so I've got a question for you, Eliza. Amongst all the different concepts you were talking about and the systems, you mentioned scale quite a lot. What do you mean by scale?
Oh man, that feels like a question that needs like a real answer. Scale is kind of, I feel this is going to be really vague. Scale is everything. It's the vibe. It's Marbo. Sorry. So it's thinking about things in terms of the passage of time and temporal scale. So what's happening, in the next hour, and the impacts of what happens in the next hour versus what happens in the year, what happens a year ago, 10 years ago, and how those things can interact and change the outcomes of events or impacts or processes. But then there's also scale in terms of just the size of things. I have no idea about the nanoscale impact of things, but I'm sure there's an impact because it's all connected. So yeah, going from that size of scale as well. So I think, does that answer your question? Yeah.
Yes. Fantastic. And so let's have a look here. So I have a question for you, James. If we did ditch the census, what would we lose?
I don't think that you'll ever ditch the census. It's about whether you create. So someone came up and asked me, how would it change how we'd use it? In reality, if you do it well, it wouldn't change anything. Nobody in this room would notice any difference. They would go to a system and they would pull up tables and they would see all the information they want to see. It's just about how you put that information into the database in the first place and how the processes you use to do that. So I don't envisage a situation, and that's why in the UK they are going to do a traditional census in 2031, because they felt that they weren't going to be able to create that set of outputs, if you like, that they would want without doing a traditional census. So I don't think we'll ever lose a traditional census. In fact, in Australia it's a legal requirement because of redistrict, changing the boundaries of the Electoral Commission. So we're not going to lose it. It's about how we change it. And in New Zealand, I think they, Stats New Zealand were here tonight and say, we are not, they would scream from the roof, we are not losing the census. We are just changing the way that we produce the information that you are familiar with. So it's not about losing the census, it's about getting it back. And in principle, you can get to a situation where you can produce this information much more regularly. So the French have a system called rolling census. So they're doing massive surveys every year, and they're rolling their information all the time and producing new information all the time from that system.
Thank you. And Noushin, I really wanted to ask you about the bees. However, it's not your area. I want to ask you, the diabetes breath test, is that something that's near to market?
There are some groups that they are very close to send it to the market. I'm aware that even in Australia, people are doing some pre-clinical trial. But then even diabetes, it has different types of diabetes. And also we have a very diverse population, so then they have to consider that. So if I go to a little bit to details in that, there is a linear correlation between how much sugar you have in your blood and what is the level of acetone in your breath. But then that linearity will be different from one person to another person. So if I can personalize a device for myself, it will work for me. Then I eat more sugar, the sugar level in my blood goes up. In the same linear way, the concentration of acetone in my breath goes up. But then the same reading is not applicable to you, and that makes it a little bit challenging. How they can personalize it, maybe the end user will do some initial test, and based on that, the device will be personalized for you. Yeah.
Thank you. I'll stick with the bees. All right. So do we have, Fred, are we having someone run to the audience for the questions?
Come closer to the panel.
All right. So we have a microphone problem. So we're going to have people come up here so that they can speak directly and use the microphone. So, yes.
This is one for the census. Imagine I'm born in 2019. Will I be using ChatGPT to work out census data? Like 30 years from now?
Well, I guess we might be asking ChatGPT everything 30 years from now. I guess you can use. I can imagine a world where these tools will be used very effectively to query information. I'm not sure that ChatGPT. I mean, if we're in a situation where people are going to just ask a large language model to fill in their census form for them, for example, I'm not quite sure what world that is that we've now managed to get ourselves into. So I think there'll be very useful tools. I think I'm not quite sure where if I'm getting the question here, but I will tell you something where large language models are very helpful and AI is coming in is through this imputation work and how coding of data. So there are still questions in the census where you can type things in to describe your occupation, for example, and coding that information. And large language models are becoming very helpful to do that and to be able to change the information that someone naturally types into the coded information that you would like. So I think if we continue with a online self-completion form, I would like to think the form will become much smarter over time as a result of these things, and that maybe even we would get to the point where you would just, describe your household and it would turn that into the information in the form and then throw it back to you for you to check and correct. At the moment, one of the reasons the form isn't as smart as it could be is because lots of households do still do it on paper. And if you don't want to create unusual effects in the data, you can't make the online experience too different from what it's like to fill it out on a piece of paper. So the most smart thing about the online form is you tell it how many people you've got and it makes enough people for you. And obviously if you have a paper form, that's an issue because the paper form only has a certain number of people on it and you don't just magically add more people on a paper form. So the online form is not, I don't think, as smart as an online form could be at the moment, but that is partly because many people do still do it on a piece of paper and you don't want to create those weird effects. That probably wasn't an answer to your question, but it was the answer that I wanted to give. So.
All right. Oh, did you want to say something?
Yeah, I have a question for you, Dane. How do you plan on making quantum technology work in room temperature?
So it does. And it does, so the thing that sets the temperature is what's the energy spacing between the two levels you care about. So it turns out that temperature has an energy. Temperature is energy. It's how much energy is there in a system. And in a quantum system, you want the thing to be very strictly stuck in the energy state that it's currently sitting in. And so to do that, you need to separate the discrete states far enough so that the temperature doesn't drive transitions between those states in ways you don't like. And usually what sets the temperature, what sets the separation is how small you can confine something. And so molecules are nice in that regard, because if you think about the size scale of a molecule, in one of the directions it's an atom, in the other direction there's a couple of atoms. It's about as small a thing as you can reasonably make. It's quite hard to design and artificially engineer something of that scale. So even quantum dots, which is where you put a metal gate down on top of a semiconductor and apply voltages and try to trap an electron into space, those wires are tens of nanometers. The dots you form are of that same sort of size scale, and so the energy gap is much smaller. The temperatures you have to go down to stop that unwanted excitation between the states is much smaller. Yep. So that's one of the reasons I really do like molecules, though, because it naturally gives you that room temperature operation. And I do think if we are to have the pathway it leads you down is to say, if you can get a quantum system that operates at room temperature, then I think there's a lot more applications for it than even the ones we're thinking of now. And we might find really cool and fun things to do with it, rather than having to carry around a dilution fridge. There's absolutely a place for that. There's a place for doing large-scale quantum computing. I don't think we'll do that with molecules, but sensing and small-scale systems where we will find applications.
Thank you. We've got a question here, so say who it is you want to ask.
This is for Professor Dan. Can the theory of superpositioning be used in quantum technology, and if it can, how?
Press the button. That's it.
Superposition is a really critical part of really exploiting the benefits of quantum systems. If we aren't looking at superposition, then there's a lot of things we can do with non-quantum systems that don't care about that. But so for the audience, superposition is where I lied a little bit and said you have to be in one state or the other state. It turns out if you control it properly, you can have combinations of bits of those states. And the way that the system evolves, if you can manage to put them in those states, is really where some of the sensitivities of quantum sensors, for example, comes from. And so absolutely, quantum superposition is super critical, super important, and it's the thing we use that gives us some of the value.
Thank you. Okay. Yes, come over and address.
For Eliza, how did your work on the Murray-Darling Basin affect it, and is any of that effect still happening today?
Thank you.
Thank you. So the work that I did was obviously summarising and synthesising all of the research that was done by the 4 research groups over 5 years and $20 million. And that work has only just last year is up as a web platform that I designed and built for them, that has all of the information, has all of the different reports, but written in a way that is digestible so that policymakers can use it. The idea being that they are using it now to do their basin plan review, which is currently still in, I think, the final stages of that basin plan review, which will then determine how they're doing their water allocations, how they're going to do a water trade market, and who's going to be able to buy or sell what and at what value, and then identifying areas for priority and kind of triage that list because not everything is going to be able to be saved. Spoiler alert, it's a really bleak future for the Murray-Darling Basin. I should tell my dad to move away, but anyway, he's still going to farm there. So it's right now they are using it now to make these decisions that will be in for these plans for the next 10, 20 years until they get to the next iteration of a basin plan review, which they'll do again in the future. So it's in progress. Thank you.
Thank you. Oh, we'll work out what we can do. I might stand here or something and pass it along. All right. Your question and.
Yeah, this is a question for Professor Dan McCamey. This is actually about, do you think there could be an impact from molecular qubits to molecular logic gates, the limitations that it can address, especially on the classical Boolean devices? I mean, actually the question stems from my idea of bringing the ChatGPT to cellular level, making a single cell as a ChatGPT. To whether it can be addressed.
So classical logic in sort of silicon devices is really hard to beat. That's the first thing I'll say. But there are applications where actually it's not particularly great. So things where one of the things that's really exciting in chemistry at the moment is sort of molecular machines and thinking about how you can add control elements to molecular machines. You're not going to stick a silicon chip that's many times larger than a molecule on top of it to make it controlled. So thinking about how we can use chemical elements to do logical activities is really important in that regard. Also, there are some places where sort of classic electronics doesn't work very well. So in the body is a good example of that. Our bodies aren't very friendly towards silicon electronics. And so if there are chemical alternatives to that, again, there might be really interesting niche applications for it. I wrote a paper on sort of exotonic logic last year with some colleagues, and it's a really fun read. If you'd like to, I'll send you a link.
Oh, you want another question?
Yeah, just a quick one. On that, if that application could be utilized for the optogenetics, the molecular qubits could be utilized for optogenetics.
I can talk more to you about that afterwards.
Okay, sure.
Thank you. Thanks. Thank you.
This question really applies to anyone in the panel. This is a general question, but generally in these fields of work, you might have to develop certain models in that might summarize certain data that you might use, extrapolate from, or to do pre-screening for a certain trend or whatever. So I'd like to ask, is there a particular strategy you might use to sort of assess the importance, relevance, validity of certain parameters in choosing a particular model, and how you overcome certain limitations of them?
Right. Does anyone want to grab that first? No? Yes? Oh, we have some inspiration.
Well, I use statistical significance to decide what I have in my models. Actually, when we build, it's an interesting point. When we were building the models for in Scotland, when they were building their coverage models in 2022, post 2022, they're building these fairly complex multi-level models on large data sets, and actually choosing the structure of the model is quite. It's not just a statistical thing, because you've got to be able to explain why you're saying that the coverage is. Patterns are why they're happening, and so we had some discussions there where, which effects must you have in, even if statistically they might not look sensible, because people will just expect you to have those things in because they are traditionally associated with coverage patterns. So certainly in our coverage work, it's a combination of statistically what will do a really good job of the prediction problem that you're trying to do, but also what makes sense to people in terms of coverage. And because you're going to produce these outputs by many variables, certainly the important variables that you're going to have in the outputs, you need them in the model to make sure you control for them.
Anybody else?
Could I add one thing to that? Sure. Thanks. I'm a physicist. Our job is to try to build a model of the world that describes it as best we can. And for me, the thing that talks about the validity is how well does that model, how well is that supported by experiment? I'm an experimentalist. I love to measure things. That is the world we live in. My job is to model that world, and so if they don't match, that's a problem.
My question's, I think, to only three of you. It's about what are the frontiers of knowledge of quantum processes in living things.
In living things. All right. Are we going to, would you? Noushin, would you like to know? You don't want to talk about nanosystems and living things?
So I guess I might do where we think they might occur in biology, and you might do how they might be useful. But there's a view that's reasonably well supported that avian bird navigation is driven by quantum effects in chemicals in the bird's eye, and that's there's good experimental evidence for that. There's good theoretical ideas about how that works. It's the same. Interestingly, it's the same sort of physics that underlies how my OLEDs work. It's about recombination of radicals and the spin-dependent influences of that. So that's one model. Photosynthesis, we're not entirely sure what the quantum effects are, but there are definitely quantum effects in photosynthetic chromophores. I'm sure there are other things where it's quite interesting. Dog smells, sure.
Yeah, absolutely. I think you can think about all these different property we get from nature. Let's say, like, have you ever noticed that the butterfly, the wing is colorful, but actually there is no pigment in the butterfly wing? The reason we see it colorful, again, go back to the surface is made of tiny, tiny nanostructure, and each of them, based on the size, they reflect different light into our eyes. That's why we see them colorful. Or have you ever noticed that when they fly while it's raining, they never bother that it is raining because the wing never get wet? So the reason is that the surface is super hydrophobic. And why it is hydrophobic and is repelling water is, again, the surface is designed in a way quite similar to the lotus leaf. So it never gets wet because the surface is made of, the water beads up on the surface because it's made of tiny, tiny kind of like a needle, let's say, like a bump, and then the surface area of the water, the interaction between the surface, the surface that the water is on the leaf is too small, so that's why the water is beating up rather than spreading on the surface. Or the mosquito, for example, can stand on the water is because of the surface tension, or the gecko can walk on the walls. Yes, because then at the hand of the gecko, it has thousands of the tiny spatula, and the spatula, rather than me having just one surface, imagine that if my hand was made of hundreds of thousands of tiny spatula, which increase the surface area. So if I'm a gecko, if I put my hand on the wall, it's not just like a 20 square centimeter, it is 200, even more, I think, if you do the calculation. So it's a huge surface area which can help the gecko to stick on the wall and walk on the wall. So the examples are just crazy, yes.
The only thing I would add is that the more I study biological systems, the more I realize I should have studied physics.
Never too late.
Thank you. Go for it.
Fantastic talk. Thank you so much to everybody. I have a question for Noushin. I remember when I was pregnant, I was telling one of my friends that, Australian government should use me instead of the dogs for the airport, and I can smell everything, even from the other building. So I remember you were showing that nose with the dog and the human being and the difference between the two. So did I actually become a dog? I mean, can you make a comment or a connection on that? Is the pregnant women usually feel that way? Thank you.
I don't know exactly how the pregnancy is impacting human body, but I think let's go back to why dogs can smell better than us. There are a couple of factors. The first one is we smell from the same airway than we breathe. So it's kind of, there's only air going through the same airway, and then we have to do two things at once. But for dogs, they have a separate airway. When they breathe, the air can be splitted into two ways. One is just going into the olfactory receptors, and then they just focus on collecting the data, and the other one is just doing the oxygen for the body. And then the number of the sensors they have, as I said, is like we have 5 million, they have 300 million. And then the part of the brain. But that's why they can not only collect more data, they can analyze the data better than us. You know, we sometimes smell something, but we don't remember where we knew that we know this smell, but we just don't remember where it's coming from. But they can immediately, there's a saying that if someone is in the soccer stadium and they eat a burger on that seat, let's say it's like tens of thousands of seats in that stadium, and someone sits there, eat the burger and leave, and 1 week later the dog goes there, a trained dog. The dog can pick up which seat that person was sitting. He was sitting there, he was eating burger, and he was happy when he was eating burger. So that's the level that they can, and I think it's not just simply smelling, but go back to, I don't know what is happening in human body, but I think definitely the hormones that is produced in the pregnant woman body is gonna shift the focus maybe. I think then your body would be more focused on, or more sensitive on something rather than being distracted. Maybe that's the reason, yeah.
Firstly, I would like to say it was such a treat listening to each one of you. Seriously, Dane, Noushin, Eliza, and James, wow. It was so beautiful. And I have a question for both Noushin and Eliza. Not because, we are celebrating the month of International Women's Day, but because I'm heading an all-female-led lunar space mission, 12,000 girls from 108 countries across the world. So I would like to record this message for the girls around the world. We want to create more clones like you, because when we talk about science communicators, we have less than 3% of journalists who can communicate science well. So how do we create more clones like you? And if it's okay, I can record this. Yes. What do you?
Okay, so do you want me to tell you how we can communicate science better, or do you want to have more female scientists or more?
Both together.
Okay. I'm going to leave the science part to you. I'm going to champion for women in engineering, because I think we struggle way more in the engineering sector. And to the girls who are listening, I would say it is not an option, it is a duty. So you have to choose engineering. No offense to the scientists in the room. The reason, I'm very convincing, listen to me. So the reason is engineers are designers, if you look at it that way. We design everything. Like we design roads, bridges, buildings, chairs, smartwatch, smartphones. We like X-ray machine, wheelchair, literally everything you touch and you use, it's designed by an engineer. So now imagine that when engineers sit around the table to design a new product, there's no woman sitting around the table. What happens is, even we have the nicest men in the world sitting there, what is designed is not going to serve half of the population, because it is not designed for women's body, especially if you are using it. And I always use this example. In 2018, I bought a smartwatch, and my smartwatch, as usual, I mean, Samsung is going to hate me, but they usually have the sensors behind the watch. And believe me, I know this shit, this is my field, okay? So this sensor is designed for sensing my skin, to unlock my watch if I'm wearing it. That's one of the functions. I paid for that. Same money as my brother paid for that, okay? But then the first version of Samsung watch, which I paid for it, couldn't feel my skin because it wasn't designed for my wrist. It was designed for the men who were sitting around the table, and every single time I have to tell my watch that, damn it, I am wearing you and you have to unlock. So this is a funny example. Later, 3 years later, I think Samsung, Apple, all of them changed their design. But the story can become very, very scary. Let's talk about the seat belt. So the seat belt, if you know, women have, and that's the statistic, 47% higher risk of getting injured in a car accident and 17% higher risk of being killed. Is not that because we have a more sensitive body. It is because the seatbelt is not designed to take an action. The airbag is not designed to open and save my body, because when they've done the test to get the approval, they've done the test on a dummy, and that dummy was yay tall and yay heavy, and then they got the approval. So when I am sitting behind the steering wheel, and if there is an accident, the seatbelt doesn't work, and the airbag doesn't work. Why? Because when they designed it, it was all men sitting around the table. So I can talk forever about all these different examples of why we need women to do engineering. It is not an option. I know everyone tells you choose whatever you like. Nope. You have to choose engineering. We have work to do. We're not there yet. We don't have that luxury yet. Okay, we solve this problem, and then the next generation can choose whatever they like.
Counterpoint. No, I agree with absolutely everything. They were the exact same things that I was going to say about the seatbelt. As far as I'm concerned, we are half the population. We deserve a space in the room just as much as anybody else. We deserve the same kind of opportunities as any other male. So I think it's just as important that we're in the room at the same time. And it's not engineering, but it's also important. If you look at any of the research that's been done in terms of health as well, most of them are focused on male outcomes, male patients. And so, you know, things like heart attacks and cardiac disease present differently in women. Even treatments for basic things like depression and anxiety. Even my own personal story, I have multiple sclerosis, and the diagnosis of that was harder than if I had have been a male presenting with the symptoms that I had, because it was too easy to dismiss it as all these other things that it could be, because women just are like that when it's that time of the month. So I think it's imperative that we are in the room just as much, just as equally represented, which means get into STEM, get into science, maybe engineering. No, definitely engineering. And I'm learning physics as well. We get into physics.
Sorry to change the subject, but Noushin, just about something, a clarity about the Nobels, because in 1915, now this is a year after eventful koala started the First World War, but in 1915, Lawrence Bragg at 25 won the Nobel Prize with his father. That was the first Nobel that Australia had won. And I think the graphene guys, who would have used Bragg's equation quite a bit, and he did conceive of the equation in his head when he was 22, right? But I think that, but of course the youngest Nobel is Malala, a woman. Yes, of course.
I should have clarified that.
No, Lawrence is physics.
So based on what I know, the PhD student who got the Nobel Prize at the age he was 27.
No, he was about 36, I think. And Lawrence is 25. Lawrence was 25
Okay.
in 1915.
Sure. Yeah, I'm going to double check it. No, thanks for letting me know, because otherwise I would have given this talk over and over and I just keep telling people this is the...
There's a woman who is the youngest, and it's Malala.
Okay,
and
yes.
A very important person in what we've just been discussing.
Absolutely.
The education of young men.
Absolutely.
Thank you very much. You're all such fabulous communicators, and this is for anyone on the panel, if any of you want to take it. We live in a pretty scary time when it comes to innovation, and when you're working in the frontiers of science, as you all are, I imagine you think a little bit about how the R&D work that you do is going to be used. And I wonder, do you feel like you have any effect on that, how it will be used by people and humanity? And do young people coming through have an opportunity to actually do something about how their work is used if they're working within science, engineering, and all of that?
Okay, so who wants to take? Yes.
I can touch on this briefly from work that I did when I was working at the Queensland Brain Institute. I was working on missile and anti-missile technology for the US Department of Defence based on bee behaviour and how aggressive bees track moving targets. I was quite young when I started that work, and I thought, oh, this is really cool, and the defence side of it was highlighted a lot more than the offensive side of the application of that kind of thing. But the more that I was doing that work, even though it was really cool seeing how these organisms were able to predict where something was going to be able to intercept it, where that was going to end up didn't sit well with me. And even though I was quite young, I was only in my early 20s, it still felt like I had to question, am I pro-war? Is that what I am now? And so I finished up with that project, but I realised that, I think I needed that point to be able to figure out where my line was of what I wanted to do. And even though it was a great opportunity working with incredible researchers that I'm still so pleased that I worked with them, I had, I guess, the luxury at that point to make the choice to move on to something else and to go a different way. But I think someone else might have a better appreciation of what to do with your tech as it's going somewhere.
I might do a broader answer if that's all right. Control is hard. When you develop something and put it out, you're developing it primarily to put it out in the world. And once you've done that, it has a freedom of its own to go off and evolve and do what it does. So that's, I think if you want to entirely control something, then you're not ever going to share it. And that's sort of the opposite of what we're trying to do as people who are in discovery and sharing that discovery. If I take off my researcher hat and put on my research administrator hat, I think quite a lot about this. Some of you may have read articles in The Australian yesterday about some researchers engaging with countries that we may not want them to on areas we may not want them to. We work very hard to try to upskill all of the researchers in my institution to be very mindful up front of the dual uses of the technologies they're developing and where they might and might not want to be doing that sort of work. And we in fact have a very formalised risk assessment process that escalates the sorts of research that might have unintended dual use applications to people who are more senior decision makers unrelated to that work to have input into should we do it or not.
Okay. Oh, more questions or answers rather.
I mean, not perhaps so much defence, but I think we're seeing in this push for large language models and that kind of technology, we're seeing that, quite frankly, most of the companies that are doing this don't give a toss about what may or may not happen with them, and they just want to get it out there and get to the front. And I teach a small subject on science and big data, and it's really more about the ethics of doing stuff. And trying to say to people, just because you can do something doesn't mean that you should do it. and thinking a little bit more carefully about, what can happen when you do it. And certainly in the work that I do with government statistics, they're very careful about how they would use any information. Much more careful, I think, than most people. So most people get very antsy about telling the government anything, but quite frankly, the government are the least of your worries, right? They look after your data far better probably than most of the other people that you quite openly give it to on a daily basis without thinking about it.
We have a question.
How good would Facebook or Google be at doing the census?
They'd be excellent at doing a census of all the people who use Google and Facebook, but they'd be absolutely rubbish at doing a census of the people who don't actually use Google and Facebook. And I guess that's the hardest thing about government statistics, is the government's supposed to care about everybody and not just, whereas the company wants to extract as much information as it can from the people it has, and it doesn't really care. Facebook can't make money out of people that don't use Facebook, so don't care about them, but it wants to get as much as it can out of the people who use it.
I might add that from my reading, Facebook does have shadow profiles of people who don't use Facebook that they get from the phones of people who do use Facebook. So they have a profile on almost everybody. Second question.
This is for Professor Noushin. Are the specific parameters and processes needed to change graphite into diamond, considering that they are almost like, they are really, really different in their molecular density and all?
That's a brilliant question. So we do have a machine in the lab that you can make diamond out of methane gas, because methane has carbon in it, because methane is CH4, so there's a carbon element. But then it should be in a very, very controlled environment. So we have very controlled environment in case of the purity, like there is no other gas molecule is allowed into that tiny chamber that we have. And then we have a very good control on how we can break down one methane molecule into carbon and hydrogen, and then how these carbons are gonna grow. So because diamond, the structure is quite different. Naturally, people find diamond naturally in the nature, and that's happened based on under too much of the pressure that the carbon handle in order to, the carbon is facing in order to be restructured into that different crystal structure. But in the lab, we grow diamonds, so we have a control on that. Methane, decompose it, hydrogen out, carbon is there, and then we, based on the control, we have that carbon atom to sit right here, and then the next one come and sit right. So we kind of manually lead carbons one by one to sit in a very specific structure, which is the crystal structure of a diamond. But in nature, it's happened when there is under too much of the pressure, so they don't go into the very normal, let's say, usual structure, and they become graphite. They be sitting in quite a different structure because of the pressure, and then they become diamond. But if you ever want to, you can come over. We make diamond every single day. We can make you rich. The only problem is a nano diamond.
All right, we have the last question.
Thank you all. Professor Nasiri, the question of smelling and a machine to smell. Now, a dog may have way more olfactory cells than we do and a proportionately larger brain. Actually, probably an absolutely larger brain than many people, actually. But where bees are concerned, they could have very few olfactory cells and have very, very small brains. Why is it so difficult to make a smelling machine? I mean, it would seem like an easy piece of technology, but why is it so amazingly difficult?
So in order to make the smelling machine, and it's called nanoelectronic nose, they call it e-nose or electronic nose. So you need arrays of sensor. So not only one sensor can do the work for you, because it's almost impossible to make one sensor that can only detect one molecule and no reaction to no other molecule. For example, in human breath, we have more than 2,000 different types of molecule. And then in order to pick acetone, of course, to simplify it, I showed you there is one sensor, and this sensor is sensitive to acetone, but what about the other 1,999 molecules, type of molecules in your breath? How my sensor is not gonna see them and is only seeing acetone? Almost impossible. Especially when you go to the parts per million or parts per billion, you are dealing with every single, let's say, foreign interfering molecule in the system. So the way we can solve it is that you come up with, let's say, I'm talking about like 28 sensors. Why I'm saying 28? Because this is something that NASA is doing. So they have 28 sensors. And they come up with this idea that each sensor is going to pick up 2 or 3 different molecules, because it's impossible to pick up only one. But then they collect the data of each individual of this sensor, and that's just the hard work in the lab. Gas 1 goes in, they see how this 28 sensor is reacting with this gas 1, gas 2, gas 3, all the way. And then they give all these data into a brain, and that brain is the algorithm that is written. And they keep testing all these arrays of sensors towards different random combination of gases, and they keep correcting or improving the algorithm. And then they get to the point that in the laboratory, now you have an unknown mixture of gas. You know each of your sensors, how they're going to behave towards which gas and which concentration. And then you can say what gases were in that combination and then what concentration of the gas. But now imagine there's a naughty student and they just add one additional gas into the system which you've never tested. How your system is going to figure out that there is an interfering gas, an extra one. So I think it is quite difficult, because then you have to write an algorithm for each environment. Like, for example, right now I'm working with a company, actually 2 companies. One of them is a big company. I think that's my destiny. I think I can't skip that. I'm working with 2 companies. They're both Australian. One of them is Accent, and what they do is that they detect pregnancy in cows using their breath. And they know the biomarker. And they realize that they can detect it way, way earlier than the normal testing. But there was a lot of hard work behind that. But the question is, if I take that sensor and system and then go to another system, which is my second company, they wanted to detect whether the queen bee is alive in the hive or is dead. So if I take that one to the hive, can this sensing system detect whether the queen bee is alive or not? No, because now I have to start again. I have to train my sensors one by one based on what gases exist in the hive, and then test it. And now my sensor can pick up if there is a pheromone release from the queen bee, so then it can tell me whether the queen bee is alive or dead. So you can do that, but then it's going to work. At this stage, it's going to work for that system that you've been working on, and whether you can just take it and use it for another system. Because of the different gases you're testing, I think it would be you're not going to start from scratch, but you have to train your sensors and write your algorithm, or adjust your algorithm again.
Yet small animals can scent a lot of things.
Yeah, but then they are targeted, they are trained. So I don't know how the bee's brain work. That's quite fascinating. We have a team at Macquarie, they're just working on how bees are communicating based on their brain. But I think even dog, if you don't train the dog is not going to pick it up. You have to train them, you have to kind of The same as a sensor. So we design the sensors, they are as a platform, but they're not working for you unless you somehow train them for the purpose. Yeah.
All right, that's all for the questions, and yeah, I'll pass things on to David.